Así que continuamos. Si quieres, Bernardo, que te tengo aquí próximo.
Desde luego, Bernardo Vargas Ángel, estoy trabajando, colaborando con el proyecto en Culebra, ayudando a coordinar los trabajos de restauración y monitoreo que se están haciendo en esa zona. Acabo de empezar el trabajo hace un par de semanas. Antes estaba en Hawái trabajando con monitoreo de corales y con trabajo en cuencas en Samoa y en Hawái también.
Mike.
Good morning, everybody. And I do apologize. My Spanish is quite rusty. And if we could do the presentation in English, I would appreciate that. My name is Mike DeManch. I'm an environmental scientist with the Horsey Witten Group, located in Cape Cod, Massachusetts. I've been working with the ICL, and we've been working with Carlos on some watershed assessments in Puerto Rico, St. Thomas, St. Croix, and a couple other spots in the area. So I'm excited to hear today's presentation.
Saludos, Loderay, si puedes continuar.
Hola, claro que sí. Hi, my name is Loderay Bracero. I'm working with the USDA Caribbean Climate Hub. I'm the new Geospatial Information Manager. So I am a fellow. This is my first workshop, so looking forward to it and nice to meet you all.
Gracias.
Gracias a ti.
Continuamos con Carlos Robert.
Sí, saludos, buenos días. Carlos Robert Colón. Yo soy ingeniero en el Departamento de Mitigación de Riesgos de la Agencia Federal de Manejo de Emergencias y FEMA. Buenos días.
Gracias. Si continuamos, tenemos a Nanette.
Nanette puso algo en el chat, ¿no? Nanette Torres, también estoy con RCS, just graduated from Mayagüez in civil engineering. Now, new conservation engineer hired in a civil field office. Está con Alberto entonces.
Gracias, Nanette. Y por último tenemos alguien que tiene el nombre de iPhone L43.
¿Me oyen?
Sí.
Saludos, es Gabriel Román, trabajo con RCS en la oficina de Mayagüez. Disculpen que es que coincidió con un Active Shooter Training que tenemos acá en el área y entonces estoy desde el teléfono. Pero nada, voy a estar aquí pendiente a la presentación. Nos interesa mucho, ¿verdad? Como dijo Alberto, pues es algo que un problema que tenemos aquí en el área, también de Mayagüez, en los pueblos que cubre la oficina de Mayagüez y San Sebastián, que es donde trabajamos, y pues estamos en la mejor disposición de lo que podamos ayudar y en términos también pues de poder absorber la más información posible y trabajar juntos en esto de erosión en los caminos de la isla.
Thank you, Gabriel. So before officially starting, I want to, if everybody can turn on their camera so we can take a screenshot for the record, that would be very good. So I don't know if Gabriel will be, or Nanette, so let's go.
No me está permitiendo hacerlo.
Okay.
Not being able. Okay.
So everybody, 1, 2, 3. So we're good to go. Carlos.
Bueno, buenos días, good morning, everybody. Pleasure to be here this morning, and thank you for showing up to this workshop. We have scheduled this workshop to last 2 hours. We'll see. We'll see what we get. I want this to be as interactive as possible, meaning with you, the audience, right? So once I start going with my PowerPoint, if you have any questions for me of what I'm discussing at the moment, please you can interrupt me, right? You say, Carlos, I have a question, and then I'll attend you, or write something in the chat, and then Yaciel is going to be monitoring the chat, or if you raise your hand, and then I'm happy to interrupt what I'm saying, right? This is for you, right? So I want to make sure that we convey the information that you need. And if we slow down too much, then probably we would like to hold the questions until the end. But just start with that. A bit of on the background of a bit of my background, right? I'm a professor in the Department of Geography and the Environment at the University of Texas at Austin. I'm trained as a geologist. I'm a product also of Mayagüez Colegio in Geology. I did my PhD at Colorado State University in the Watershed Sciences program. I tend to call myself a hydrogeomorphologist. I like really applied stuff. A lot of my science, the science that I do, is triggered by management needs, right? And what you're going to be seeing here is a product that comes out of that, right? So I'm interested in stuff that has to do with hydrologic processes, geomorphic processes, but I like to do that kind of work as it relates to human needs, okay? And you heard from especially NRCS guys and those working in Culebra how important this problem is. I'm not a modeler, so I'll give you that up front, right? And what you're going to be seeing is almost like an initial attempt trying to model things that we have been measuring, right, in the field, right, and provide some context to our monitoring and also our experiments that we do in the field. The model comes out probably like 2017, probably. Actually, after that, I think it was that fall during Maria. I was here, of course, in Texas, and I had the time to work on this. It was an extra component to a project funded by Univ, the National Fish and Wildlife Foundation, that happened that was targeting in an area in Cabo Rojo called Los Pozos. So what you're going to be seeing, right, in terms of the products that come out of the model are only based on work that applications of the model to Cabo Rojo. Okay, we are in the process still of adapting the model to Culebra. And also to the coffee farms. We're using Hacienda Candelaria in Yauco as an area. So the model is still experimental. It's in developing stages. I'm the only one that has actually put his hands on the model so far. And so it's still not ready for prime time, right? I don't feel it's useful for the purposes, I think, of us, right? I mean, Bernardo's needs in Culebra and those for Alberto and Dolores in RCS. So it's ready for that, but it's still I want to be in control of how it's used so far, right? I don't want to just release it and allow people just to use it because I want to be very careful with that. We will not be running the model today, so you're not going to see a live run on the model. And I have part of it is that's going to change as I adapt it to coffee farms and Culebra as well. So model takes a series of routines. It takes maybe 10-15 minutes to run, right? So I didn't want to waste the time doing that in the limited time that we have. But you're going to be able to see what it requires. You're going to be able to see the capabilities of the model and the pros and the cons of applying it. Okay. So I'm going to share my screen. And again, right, feel free to interrupt me anytime, anything that you don't understand. If I freeze or something like that, please let me know, and I'll repeat what I was just saying. So okay, so RoadConnect, and again, right, I mentioned that some of the work, some of the stuff they're going to be seeing here was in part sponsored by Univ, but there's a lot more, and I didn't want to just list everybody here. And then this is definitely right, the collaboration with Protectores de Cuencas as a recipient of these awards, and then providing help with the logistics and finances, managing the finances of the projects. So a bit of an overview of what I intend to cover today, right? I want to a bit describe why do this, and probably maybe this audience doesn't need this introduction, but I just want to go over that as well, because maybe we're not really aware of other potential uses of this kind of modeling. I want to present the advantages and also the disadvantages of using RoadConnect. Okay. Describe the science, what goes behind the scenes, right? And how I use the science as part of the model. What it takes in terms of the model inputs, right? This is an ArcGIS-based model, so the geodatabases that are required. Present the general model structure, what it's doing behind the scenes without all the details, because then that's a bit too heavy, right? And that would take a very long time. And then also show you what it produces, right? The types of outputs that you can get out of this, and there's diverse type of outputs that it produces. So in a nutshell, what does the model do? Okay, it takes 3 shapefiles. Okay. 2 of those are lines, okay, line type of shapefiles, road segments, of course, flow paths, and I explain what these are, and then points, which I'm calling here drains and nodes, and then I'll explain that in a while. It also takes in, if it applies, a retention pond volume database, okay, and very simple. Okay, this is just a database, doesn't have any special reference. And then as you begin the model, the user is asked to enter a particular storm size in terms of how millimeters of rainfall, okay? So the model runs on a storm by storm basis. Okay? What does it do? It estimates both runoff from roads, and also in the next version of RoadConnect, especially for coffee farms, it also is going to contain estimates of cultivated land and forest land runoff response. The same thing with erosion, with sediment production. Okay. Runoff from where? Just the roadbed. Okay. In terms of the road, just the roadbed. It's not trying to model anything else in terms of sediment production. It's not trying to estimate cut slope contributions, not trying to estimate any gulling that's happening below the road. Okay, it's just the roadbed, just the travel way, right? The drivable surface. And then it does, and this is the most complex part of the model, is that it tries to convey, right, that runoff and that sediment to downstream sinks. Okay, so it tries to calculate how much of that runoff that is generated at the road surface is actually being delivered downstream to what are sinks. This could be a stream, this could be a lake, or this could be a coastline. Okay, and I'll tell you a bit about what exactly, right, at what scale and in which context this could be applied. And then it also keeps track of the amount of sediment that is actually being accumulated in sediment retention ponds. Okay, so these are some of the products that come out of the model. Why study sediments, right? Why do a model on erosion and runoff? Okay, and one of the first reasons, and this connects directly with the original objective of the model in Cabo Rojo, and then also the work that, for example, Bernardo is doing in Culebra. Okay, sediments are a key pollutant and considered a major threat. It's not the only threat to coral reefs in the Caribbean. Okay, but the corals, as we probably all know, haven't been doing well at all, and they haven't been doing well since we actually started documenting them in the 1960s and 70s. So here, right, just to give you a quick view, this is a work that was done by Bill Jackson out of the Smithsonian Institute, right, collecting all of the data from throughout the Caribbean. These are regional curves. Okay, this curve on the left represents a combination of data from St. Thomas, USVI, Costa Rica, Jamaica, Belize. Right, this is percent light cover in the 60s all the way to the 80s, and the 30s, maybe close to the 40s, and then by 2011, about 10% left, right? And this is a regional scale look. Okay, this curve on the right, B, are trends in coastal Mexico, Puerto Rico, St. John, St. Croix, and the Florida Keys, right? From 30-something% down to maybe 15%. Okay. When we look at it closely, right? This is the case for the U.S. Virgin Islands. It's the same curves, right? But specifically for the different islands, right? St. Croix started in 20-something%, dropping down, right? So the same thing in St. John, even though we have a national park there. Right, and similar trends in St. Thomas, and then that combined, especially in St. John, right, you can see the increase on microalgal cover. How about in Puerto Rico? Same thing, right? Maybe more abrupt curves here, right, just because of the type of coral that used to dominate in Puerto Rico, the elkhorn that provides a really good cover. Okay, so areas in Culebra, Guayama, Mayagüez, Vega Baja, right, you can see them just plummeting down. Okay, from the 80s down up to 21st century. And then this is a close-up look at coral reefs near Fajardo as well, just plummeting down. Okay, and sediments being one of the stressors, right? Not the only stressor. To what degree do sediments affect corals? At the experimental level in a lab, you can isolate the effect of sediments. We still have not done a really good job combining watershed with water quality and coral reef response within the U.S. Caribbean, and that's something that Caroline Rogers, my colleague and good friend from St. John, and myself kind of discussed on this paper, right? Yeah, we know it's a stressor, but to what degree it actually affects corals nowadays is something that is still a research question, right? And hopefully the idea of the model, especially applications like in Culebra, is that maybe the model can actually help start addressing some of those issues, right? It's really expensive and logistically complex to maintain a very long-term monitoring program at the watershed, in the coastal water system, and then also with the coral reefs, right? So maybe the model can help us fill in some of those gaps. Also, and this is something that I think when we discuss sediment issues in Puerto Rico, we tend to overlook. But it's a real problem. It's freshwater quality. Okay, somehow nos acostumbramos a esto. We got used to this at some point in time, right? Rivers shouldn't look like that. Rivers don't look like that. I mean, even in other tropical areas, right? Naturally, they don't look like that. And even on some areas that are being used by humans, right? That's something that we need to think really deeply as to why we got used to this. But There's challenges, right, to water treatment and distribution that are tied to high sediment loads. This is exactly what this news story is telling. Okay, one of the main filtration plants in Puerto Rico being unable to process water just because of the high loads of sediment. Okay, and then something that we really don't talk about, and this is something that is almost a gap in tropical systems, especially in Puerto Rico, is that we really don't know what kind of impact sediments are having on stream ecology, shrimps, and other benthic organisms. Another reason to do this kind of work is sedimentation of water reservoirs. Okay, we really don't know the state of our reservoirs, but we presume that right now, overall, right, the specific reservoirs that we know where they stand in terms of water holding capacity and sedimentation. But for many of them, we don't know, and that's work that we are actually doing out of the University of Texas as well. But we presume that about a third of the water holding capacity, right, the design capacity is gone, right? It's occupied by sediments. Okay, and of course, right, erosion affecting soil. Okay, and the ability of soils to actually maintain vegetation and maintain a crop. Okay, but this is something that the models wasn't really thought out. It doesn't come out from that need, right? And that's something that, again, we could talk with the folks in RCS how to enhance that, right? That capacity of these types of models to do that. Why the emphasis on roads? Okay, and what you're going to be seeing for the next few slides is work that we have done throughout USVI and Puerto Rico. St. John, of course, that's where I did my dissertation work. East End, St. Croix, okay, work in Culebra, some work in Vieques, work in La Parguera, and work in Cabo Rojo. Okay, all of those have in common that they are in a dry tropical setting. Okay. And the most extreme of those settings, which is East End St. Croix, kind of looks like this. Right? That's cacti, right? Really dry conditions, in septisols, mostly in terms of the soils, ephemeral streams, which means that there's very little opportunity for the watersheds to actually, under natural conditions, to contribute runoff and contribute sediment to the marine environment. That's why we have corals on those near these areas, right? Just because that interaction with the landscape, with the terrestrial environment in terms of inputs is really limited, right? Meaning it happens a couple times a year, okay? And rainfall totals in the 800 to less than 1,000 millimeters per year.
Carlos,
Dime.
ya llevamos la primera media hora.
Perfecto, gracias. So the wet tropics, right? We have also done work in the wet tropics. Most of it has been in Yauco and Maricao, okay? And then this is how it looks, right? And you can see how much more precipitation, right? It occurs here. We have perennial streams and totally different types of soils, right? And we have worked on oxysols and ultisols so far. And then, right, those of you who are interested, we have a series of publications dealing with these issues. These are not the only ones, but please let me know if you want to get a hold of these. I'll be happy to share them with you. But a basic result coming out of all this work is that the roads are really driving the sediment budget of all of these landscapes that we have studied, okay? Road erosion rates in dry tropical settings are 10 times to 10,000 times greater than natural areas, okay? And then at the watershed scale, road erosion consists or contributes over 90% of the total sediment produced, okay? And this applies to, again, Culebra, Vieques, St. John, St. Croix, St. Thomas, Cabo Rojo, Parguera, okay? wet tropical areas, road erosion is actually has a greater effect than in dry tropical areas, up to 100,000 times higher than erosion rates. And people say, and this is something that's been very interesting. Maybe I think Atienza was there when we did that workshop on site on Hacienda San Carlos, Carlos Vega farm, right? Farmers like, most of the sediments coming from the cultivated land, and we had sediment traps on site, right? We were able to show, right, visibly that's not the case, right? Most of the sediment is coming from the roads themselves, the road network, okay? So road erosion is actually 100 to 1,000 times greater than that occurring on agricultural land, okay? And then similarly to dry tropical settings, over 90% of the sediment is being generated by the road network. And this is something that I'm not going to be talking about today, but then also roads can actually contribute to increase the incidence of landsliding. And maybe RoadConnect could actually help us a little bit understand that process, but I'm not going to be talking about that today. So why use RoadConnect? There's many other models, okay? But many of them are still improving. And there's models that are specific for road erosion, but they have not been proven or tested for our types of landscapes and climate and soils and lithologies that occur in the U.S. Caribbean. Okay, that's a research question. Okay, that needs to be addressed, right? So, and most other models do not address sediment condition from roads. Okay, roads are either ignored or lumped with everything else, right? An example of that, and this is a model that has been used extensively in Puerto Rico, SWAT model. Okay, soil water application tool or something like that, analysis tool. So SWAT, for example, generalizes, simplifies the landscape, okay, into something that is called hydrologic response units. Okay, so it lumps the diversity of landscapes that are out there, divides the watershed into those, and then makes a calculation for in terms of runoff and sediment for each one of those. Okay, so there's only one slope value, one land cover value, etc., and then just one result. So SWAT, what would SWAT do with this type of landscape, right? There's a coffee farm in the uplands of Puerto Rico, right? And what I want to point out here, right? There's obviously a different type of vegetation here. There's some probably most likely secondary forest. We have this area here, which has a lot of plantain. Most likely the soil exposure is very different from what is over here. Another pocket of early succession, right, turning into secondary forest. And then, of course, we have the roads, okay? SWAT will take all of that area and most likely areas surrounding this farm and actually lump it into one single valley, okay? So the question that I ask people that are, but we have SWAT, we have this, yeah, but SWAT would just give you a solution for that entire watershed. For that entire farm, we cannot really cure the problem, right, throughout an entire farm. That's just too costly and logistically impossible, right? So we need to find targets, okay? And then we need to find priorities, okay? And the research that has emerged over 30 years of work so far is that the roads are a priority. Okay, but then which roads? You cannot address every single one of those roads. That's too expensive and logistically impossible. Okay, so RoadConnect is trying to address that, right? Prioritize which roads actually to address for erosion control implementations. Okay. These landscapes, especially these dry tropical landscapes, are very, very sensitive. A small change and small scale disturbances can actually have a drastic impact on sediment delivery to the coastal area. Okay, this is an example from Hawksner's Bay in St. John. Okay, mostly within the park. And then here, basically, we're just showing that just a mild increase in exposed soils, construction of a hospital, some roads that exist within the watershed causes a very dramatic increase in sediment yields, okay? Sediment yields above background, okay? Over 100 times, just disturbing 5% of the landscape increases sediment yields by over 100 times, okay? This, and then, right, all of these are corals, right? And the outlet for the little drainages that come out from this watershed there's one here and there's another one here. They're right, there's a couple meters away from the outlet of these streams, okay? So very sensitive. And then what we have been promoting is that, right, sediment yield is almost a product of the density. And these are unpaved roads, okay? So as you increase the density, you increase the sediment yield. So that's the dry tropics. How about the wet tropics and the coffee growing area of Puerto Rico? There's tons of roads. It's unbelievable when you actually look underneath the canopy, how many roads are there. This was shocking to me. And this took actually a lot of time to map. We use LiDAR to map this. This is the Luquetti Lake, okay, Lago Luquetti in Yauco, okay? And then you can see, right, how many roads, over 900 kilometers of roads. And I would say about 85% of those are unpaved. Okay, these are the main roads, right? The public roads, carreteras estatales, but then everything else in brown are roads within coffee farms, just so that you can navigate a little bit, right? Hacienda Candelaria will be here. These are the Ruiz's family's farms up here, and then Carlos Vega will be somewhere around here, okay? So this accumulated impact of all these roads is really severe. Okay, so they're part of the landscape and they're there to stay. So we need to understand them. Here, a bit of the science behind RoadConnect. Where do the functions that we use to calculate runoff and erosion come from? Okay, a lot of what we're doing comes from rainfall simulation experiments. Basically, right, we bring this rainfall simulator, just a fancy shower, right? That's standing about 4.6 meters above the ground. We use a water truck to pump water into the system, right? We delineate the surfaces that we want to measure, and then we collect runoff and sediment coming out, okay? With the combination of rainfall measurements, you can see some rain gauges along the sides of the plot here. And knowing runoff, we can actually back calculate infiltration capacities, okay? And that's something that it's used for the model. So this is two different plots for a cultivated surface and a road. I believe this is for probably an oxysol or an ultisol and an unpaved road. And this is a cultivated surface mostly for coffee, okay? And you can see this is the infiltration capacity curve, okay? Very typically shaped, starts off high and it just levels out at about whatever, let's say 50 millimeters per hour, okay? This is the road surface. You can see it starts at around 50 and then just levels out at about less than 10, okay? So here, right, just to basically show you that that roads have a very limited infiltration capacity compared to even cultivated land, okay? And the natural infiltration capacity curves will be above this one, okay? With this model, then we can actually simulate what the runoff response would be, right? Let's say that we have a rainfall event for an hour. The level of 60 millimeters per hour. So therefore, the difference between the excess rainfall, right, that cannot be infiltrated becomes runoff. Okay, so that's kind of the basic concept that we use here. Okay. And then also for individual roads, right, depending on the slope, depending on the surfacing, we can also calculate infiltration capacities, right? What we see in here is an unpaved road, and then this is a gravel road. The changes are not as dramatic, but the gravel road has a slightly higher infiltration capacity than an unpaved road, okay? So far, right, we have, in terms of the data that we have to feed the model at this scale, right, in terms of rainfall simulation, we have over 100 simulations done in coffee farms in Puerto Rico, about 15 Culebra, and about 20 so far in Cabo Rojo. Okay, so we use these to create the functions of the model. Other types of measurements that we can use, right? Different scales, a well permeameter, just a borehole test. We can use flumes, right? And this is a way actually that we're going to be using to validate the model in Hacienda Candelaria and Yauco, right? To see if the model actually provides us with a realistic volume of water that's flowing out at the scale of maybe a portion of the farm. Okay, this is something that is really important, right? Just showing that the model actually provides realistic results. And then in St. John, right, we have actually monitored stream flows coming out of the small watersheds coming out. Okay. What goes into how does RoadConnect actually use this information? RoadConnect actually uses simplifies the hydrologic response by just using the runoff coefficient, and right? And runoff coefficient is basically the percent of the rain that is converted into runoff. So roads of different types, with different soils, with different slopes are going to have different runoff coefficient, and that's something that's embedded in the functions and the algorithms that go into the model. So road runoff in volumetric means, right? It depends on the storm size, okay, the runoff coefficient, how long of a segment you have, how big of a surface you have that's actually generating this runoff. Okay, very simplistic approach, right? But it's fed from actual data collected on these areas. For erosion, we also depend on rainfall simulations. Eventually, we can use also other types of data, right? This is actually part of Jaciel's thesis, using sediment traps. Okay, we have also measured sediment traps, use sediment traps to measure erosion rates from cut slopes. And then similarly to the flumes that I just showed you, right? Sediment detention ponds can be used as a way to see if the model is right in actually conveying all of that sediment from the road downstream. Okay, so we have used this to calibrate the model or validate the model in Cabo Rojo. Okay, and that is done by just measuring accumulation rates using surveying equipment. Okay, you had a brief overview of this already, but then right the impacts of roads in increasing erosion rates, right? So in the dry tropics, right, several orders of magnitude, the same thing, natural rates, and then these are roads, right? They're having a much higher effect on erosion rates, and then roads actually producing having erosion rates that are actually much higher than cultivated land. Okay, and these are magnitudes of order high. Okay, very similarly to runoff. How do we calculate road erosion? Okay, in tons. Each road type is going to have its own erosion rate. What do I mean by road type? Its location, right, which controls its lithology and soil type. Whether it's been gravel or not, how often the road is graded, how steep the road is. Okay, so all of that information needs to be given to the model, and it recognizes which road you're talking about and then applies that erosion rate. Okay, storm size. Okay, so that's a user-defined parameter in RoadConnect, and then the size of the road, right? The road surface that actually producing the sediment. Okay, I'm just going to point out that the efficiency of graveling is going to be embedded on the model, but it needs additional testing. We only have 4 rainfall simulations done on gravel roads, properly gravel roads, and that's something that needs additional testing, which means it needs additional funding. Okay, the same thing with cultivated lands, right? We have a very limited amount of data on those. And then most of the work that's been done has been done in Yauco and Maricao, especially in the coffee farms, right? So nothing has been done on the more coarser soils, right? In the vicinity of Utuado. For Culebra, for the US Virgin Islands, I'm satisfied with what we have. I don't think we need to go back and do any more simulations. Connectivity, okay? How much of that sediment that's produced on the parts of the landscape actually make it down into a water resource of importance, okay? This is one of the hardest problems to deal with in hydrogeomorphology. Okay, logistically, it's very, very hard to do. Okay, and also the physics of it, of these processes are very complex. Okay, and you can see, right, that people from the 80s all the way to recently have been trying to come up with approaches to this, and then I'm proposing a new one. Right, this is a new approach to doing road connectivity, especially with the sediment portions of this. Okay, so how does RoadConnect handle this? Okay, it's better for runoff than it is for sediment. Okay, it uses what is called the volume to breakthrough concept, and this is what the concept means. In order for runoff delivered by, let's say, a culvert, okay, up here that's a road, 2 culverts. There's a cost for that runoff and sediment to making it all the way. Let's say that's coastal waters. There's a cost, but this has a potential, okay? This has a volume, okay? So given a certain set of circumstances, storm size, the length, the surface area that is actually generating runoff, RoadConnect tries to tell you, okay, can that runoff actually make it during one single event all the way to your target or your sink? Okay, if the answer is no, then that's a 0. None of that runoff or sediment made it all the way out into your sink. If the answer is a yes, then tries to answer how much of that. Okay, always that number is going to be less than 100%. Okay, but there's always going to be some water that's going to be filtering into the landscape. There's going to be some sediment that gets filtered. And then one of the things that RoadConnect is trying to do is not only to see the filtering capacity of the landscape, right, but also detention ponds. Okay, and we'll see how it handles that. Okay, so the metrics of the volume to breakthrough concept are in cubic meters of water needed to advance 1 meter downslope. Okay, so if it costs 0.25 cubic meters of water to advance 1 meter downslope, how far can 100 cubic meters generated by a road at a culvert travel downslope? Okay, so basically this is the potential. Okay, that's the water that you have available, that runoff. That's the cost, right? You basically just divide the potential by the cost, and that gives you a total distance that water can actually run over the surface. Okay, so if a coastline is greater than 400 meters away from this situation, then you have no runoff delivered. Okay, but what if a coastline is 200 meters from the road drain? How much of the original 100 cubic meters are delivered? Okay, and basically use this ratio. Okay, this is your potential, and this is reality, right? And you solve for that, and in this case, okay, 50 cubic meters of runoff will be delivered to the coastal environment or to your sink. Okay, and the same proportion is actually applied to sediment. That is not accurate, that is not correct, but that's the best we can do right now. This will require really sophisticated experimentation. Okay, it's doable, but then it requires fieldwork. Okay, this is the best we could do, or somebody else develops an equation that we can actually rely upon. Okay, how do we come up with that number of cubic meters per meter required? Okay, that's very complex, right? That we explain how we came up with that number. This is a case we actually did some experiments in the monitoring work in St. John, and we came up with a number. this is the number that we came up with, right? And we're applying this number to, we'll be applying this number to Culebra, and then we have applied to Cabo Rojo as well. Okay, that number is very close to what they came up with experimentally. These are the folks that actually came up with that concept. I didn't come up with the concept. Jackie Croak and her team out of Australia, right? And the number that they came up with in their scenario was 0.067, which is quite close to what we came up with. Okay. For the coffee farms, this is gonna not be based on actual empirical data, but with modeling. But we'll come up with a number. My fields are gonna be much smaller. Okay, less volume of water required to transmit it downslope, just because of the texture of the soils. Okay. Now I mentioned sediment traps. How does it address the trapping capacity of sediment traps? It uses this equation. Okay, I'm going to boil it down into the essence of this equation. Okay, in the next slide. But notice this. This has not been tested in the Caribbean. Again, another opportunity to do field work and to have additional work feeding into these types of needs, right? We are increasingly relying on detention ponds, especially in Culebra, to reduce sediment delivery to the coastal environment. But we rely on an equation that actually, the essence of the equation, the parameters, right? These numbers, what does that mean? I mean, I really cannot tell you right now what does it mean, how they come up with this. This is empirical data, right? From 1953. Okay, and then revised or reformulated in 1981. Okay, so this is another opportunity for additional research, and this is type of research that National Science Foundation and those guys are not gonna fund. They're not interested in this kind of stuff. Okay, this is too applied. Okay, so these funds have to come from somewhere else. So in essence, what does the equation say? The larger the pond to runoff ratio, the larger this, right? So the very large pond, very small runoff event, so you're gonna have a high trapping efficiency. Okay, the smaller the pond and the greater your runoff input, the less efficient is gonna be a trapping sediment. Okay, so trapping efficiency depends on event size, okay, and then also the surface area that is flowing into the pond. Okay, and it also depends on what? How much sediment is trapped in the pond. Okay, so as you accumulate sediment, the trapping efficiency diminishes. Okay, and this is something that sort of manually still we can incorporate into RoadConnect. Okay, we can see how the efficiency actually declines through time. What is missing in RoadConnect? There's only one runoff generation process that we can actually incorporate it into the model. That's called precipitation excess. Basically, when it was raining harder than infiltration capacity. Okay, that's what we measure directly during rainfall simulations. That is not the only way that. Sorry, I'm watching a Mandalorian, so on the way I always hear the way and think about that. That's not the only way that runoff is generated. Actually, under natural forested conditions, right, there's other processes that actually contribute to runoff production, right? And one of them is saturation, excess overland flow. We basically saturate the entire water column, entire soil profile, and then it emerges onto the surface. Okay, that is the predominant process by which runoff is generated in most of these landscapes. Okay. But especially in dry tropical scenarios, okay, this is very, very rare. Okay, typically soils are really dry. Okay, when does this process actually when is it triggered? Whenever you have a very long event, okay, or a series of events that are in succession, right? That's where you can actually saturate the soils. And then you have this, what I'm showing here, this is in Culebra. That's very rare to see in Culebra, right? A flowing creek, okay? This is a condition in which that runoff is mostly being generated by this process and not this, okay? The capacity of the model to actually convey sediment and runoff stops at any flowing stream, right? This is not a fluvial. It's not made for fluvial sediment transport. Okay, so it's applicable to at the farm scale. Okay, this is actually where we actually manage and make decisions. So I think that's the usefulness of it. To very small watersheds like those in Culebra, like those in St. John. Okay, so I feel comfortable with the application at that scale. And it's only right now able to model for roads. Cultivated lands are going to be added soon, meaning hopefully before the end of the year, we'll have a paper kind of engaging with this. And as part of that paper, we'll provide the model with the tools that it needs to do this. Okay. It's also, right, it's a bit cumbersome, right? It's only one individual event at a time, okay? And the geodata database is when you see what it takes, right? It's still very, very hard to do. It takes a very long time to develop those, especially in the coffee farms. In Culebra, it's a bit more simpler, but in the coffee farms, we'll see what it takes. One thing that I want to show here, I'm going to step away from my PowerPoint, is to show you a product that this is ready to go, and we'll share it with you guys, Alberto and Gabriel and whatnot. This is something that we came up with as part of this Univ project to actually help you try to make estimates of runoff production from coffee farms and also sediment production from coffee farms. Okay, and at some point, dime.
Sí, tenemos una hora.
Okay, perfecto. We're good.
I'm gonna share the link to this spreadsheet in the chat as well.
Okay, and then you'll have access to the PowerPoint. Okay, we'll be sharing that with you, and then you see that my slide has the link to this spreadsheet. Okay, so this is something that has all the functions, and again, these are all logged, but this here has all the functions that I was talking to you about in terms of erosion and runoff and infiltration capacities and whatnot. So that's embedded in here. Okay. Now, I'm very simple to use as well. Okay, and at some point, Alberto and Gabriel and whatnot, we should sit down and see what you think about this, because I mean, I know you use the curve number method, but and we would like to compare and see how useful this is for you. So for example, first thing that you do is you choose your, and this is not RoadConnect. This is not RoadConnect. This is an Excel spreadsheet on its own. Okay, you choose the general area that you're working on. Okay, so here we have, right, Juntas all the way to Maricao. Okay, this is feeding off data from the weather service, okay, that and it's feeding off from 3-hour duration rain data. Okay, so let's say that we're working, your farm is in, let's just say we're in Maricao, in Mira Alta, and you want to model a runoff event that happens, has a recurrence interval of every 50 years. Okay, and you can see you can choose from 1 all the way to 100. Okay. And again, these are 3-hour duration data. If you guys use a different duration for your modeling and your estimates, it could be easily adapted to this. That should not be a problem. That's the kind of conversation that I want to have with you. What is the predominant soil type? Okay, we only have here what we have actually done experiments on. So multisol, oxysols, which they seem to be responding very similarly, and then insecticides. Okay. How much, right? Let's say you have a farm that's draining into a spot where you want to design a culvert. How many roads do you have above that? Let's say that we have 2 kilometers. What's the average width of the roads? Let's say 4.5 meters. The predominant road surface. Okay, then I'm gonna move here. Is it mostly ungraded? Is it just freshly graded, or is it gravel? Okay, you choose. Let's say it's graded, recently graded. These are going to produce much more sediment than an ungraded or a gravel road. what's the size of your farmland area? Okay, what is the cultivated land? Let's say that we have whatever, 3,000 square meters or something like that. Okay, and what is the predominant soil cover? Is it bare or vegetated mulch? And then again, you have visuals to kind of guide you to what this look like. Okay, let's say it's bare. Let's make it as nasty as possible. And then you have whatever, 3,000 meters of forested land, upstream, upslope from you where you want. Okay, calculates, right? It gives you immediately, right, the maximum rain rate. So right, this is the rainfall. Okay, it gives you runoff rate from each one of them, and then also total. Okay, so for example, for this event, and I'm gonna stay too long here. I'm just gonna show you this, right, and then we can talk about it later. But it gives you a total volume. Okay, it's also useful for designing like detention ponds and that kind of stuff, right? And then the maximum flow rate into the pond. Okay, and then gives you the amount of sediment that's eroded and the amount of sediment that should make it into that spot. And again, this is not RoadConnect, but we did this as an aid, considering the needs that you have for modeling this kind of stuff and seeing how this compares to the actual methods that you have that you use nowadays. Okay. Okay, so
Tenemos una pregunta de Atienza que levantó la mano. Adelante.
dime, Berto.
Yes, Carlos, just a quick question. I really like that spreadsheet. Is that something that we can expand to the whole Puerto Rico or Caribbean area? Because I see it as a good tool for, let's say that island-wide, we want to rank farms and we want to address the farms that are eroding the most, and that way we'll have a way to, that we can rank them.
That's a good use of this, but then remember, this is just calculating how much runoff and erosion is generated. It's not, and that's why it's different from RoadConnect. It's not connecting that into the receiving waters or streams. Okay, so still the use is visible now. This what you're seeing here is feeding off only the rainfall simulations that we have conducted in a very restricted part of Puerto Rico. So in order to do that, then we will need to either replicate that or have data that actually we can trust to do that. I mean, again, this is our oxysols, ultisols, mostly from upper Barrio Rubias and Frailes in Yauco, and then Indira Alta, Indira Fria in Maricao, and then some insectisols that we ran into in also in Yauco, in Aguas Blancas, right? But again, yes, it's possible, but then we don't have the data for that, Alberto. No tenemos los datos para eso todavía. But
all right, yes, thank you so much. That's really interesting.
The potential is there for that kind of stuff, and
yes.
that's the whole idea. And then for us to talk and come up with something that makes sense from the perspective of science, but also from the perspective of your needs, right? So this is supposed to be customized for you guys.
Absolutely, thank you.
Okay, so what does it take? Going back to RoadConnect. Okay, what does it take? And there's right, this again, you can click on this and that will take you to a lot more detail than what I'm going to be presenting here as to what the model does and the inputs. Okay. Now, important for RoadConnect, and again, I don't want to get too technical, but everything is fitting off, right? You need to put this folder, you need to create this folder called RoadConnect in your C drive, and right, that you immediately see why this is I'm a rookie at modeling, right? So a very sophisticated model will actually create this kind of folders for you, and then it needs a series of folders named as they appear here, right? Right now, some of these are gonna change slightly when I for the next version. Okay. The essence, right? And you need 3 shape files, okay? Drains and sinks, flow paths, and roads. And then you need also this a table, right? This is a DBF table called pond volumes. Okay, so that's the essence of it. Okay, and then this is how it looks, right, when you're putting everything on ArcGIS. Okay, roads. The roads have to be split, right? So you map all the roads. You can use aerial photography. You can use LiDAR, right? LiDAR shows everything that's on the canopy. So the combination of both is what I would recommend to do that. And then if you can go to the field, you can map the drains, and actually you can do sketch maps of how water is flowing, right? You want each segment to be hydrologically consistent, meaning, like for example here, let's assume that this is draining this way, right? The slope of the road is actually this way, and there's a drainage point here that's taking all of the runoff coming from above and then forcing it off to the side here. Okay, so this is the end of a segment and the beginning of another segment, and then there's another drainage point here, and then that's the end of that segment. Okay, so that's that segment, right? Is represented by a line here. That segment is represented by a row here. Okay. Important sort of details that attributes, right? Characteristics that are stored in this, that must be stored in this shapefile, right? This is a shapefile. The road length, you allow ArcGIS to calculate that for you. Okay, the road width, right? That's something that you can either measure in the field, or you can actually use their photography or the LiDAR DEM to help you with that. Okay, so those two are relatively easy, and then the area is just a product of those two, right? This one here is gonna change. Okay, this was done for Cabo Rojo, right? And it was a very small area, but then the lithology was totally crazy there, because you had from shale to serpentinite to limestone and half a mile distance from each other. So that was really interesting. But then here, right, what is going to go here, right? I'm thinking about calling it substrate, right? Is what kind of soil you got. Okay, and then also whether the road is graveled or not. So I'm thinking about having this combined types of characteristics actually in there, right? And for a farm, for example, you're applying this to a farm, then it's going to be the type of soil most likely is going to be consistent, right? So you're not going to have that much variability, but that information must be embedded in that type of attribute. Okay, and then drain ID is basically, right, this road segment. I'm calling it that it ends here and is draining to this segment, right? So this segment, whatever it's called, it should have in its entry here in its drain ID should have LP_29. Okay, so this connects to that. Okay, so that is the road input necessary. Flow paths. Okay, flow paths is something that we rely on ArcGIS to do for us, and it's some of them sometimes you need to edit a little bit, but you rely on the digital elevation model to create these. Okay, and basically for every drain, so for every road drain that we see here, right, each drain is going to have a flow path. Okay, so you use topography to let the you use ArcGIS to let it map the flow path. Okay, so then, for example, for a drain exists here. That drain would just force all the runoff into this area and then join this other flow path here and start coming down. Okay, so you can see what the flow path is saying. It's just tracking the distance, right, from your source, from where road is dumping water and sediment. Okay, and it's telling you where it goes. Okay, two attributes that are important here. Okay. The drain ID is basically what's a drain that's leading into that flow path. Okay, what is the point? That's or node. Okay, it needs to know that name. and then its length. Okay, if you remember what I was talking about, the volume to breakthrough concept, that's where that distance comes from, right? Can you actually overcome the distance required, right? For this runoff, for runoff that's delivered here by a road, can it actually make it all the way out into the coastline? Okay, so again, this is another type of input. Okay. The drains or the nodes, the points. Okay, there's 5 different types of points. Road drains, the culvert, the cross drain, the point where runoff actually exits the road system. Connectors, where 2 flow paths meet. Okay, for example, I'm not showing all the points here, so that's a connector right there. You see there's a flow path that's coming through. Okay, there's another one coming through here, and they meet there. Okay, so that's a connector. Sediment retention ponds, we got 2 here. There's one here, there's another one here. Okay, so those are identified as well. Okay. And end nodes, these are the ones that are actually connected to your sink. In this case, the coastline. Okay, so these 2 are end nodes. Okay, what goes into this database? This is hell in ArcGIS. This is the hardest part in terms of the time and level of concentration that it requires, because it's being done manually at this point. Okay, and basically what you need to do, okay, these are points, and the points is really easy, right? Not really easy, but you can use contour lines, right, and the topography to actually guide you through mapping those. Okay, or if not, you rely on mapping at least the road drains in the field. Now, each one of them, you can see that the attribute table is a bit more complex. Okay, it's got its name, its drain ID. Okay, and again, the drain ID is a way to connect the road inputs, right? What's coming, what I calculate from the road shapefile into this database. Okay, and it also connects with the flow paths. Okay, so this is what's tying up this database with all others. Okay. So drain IDs, right? It tells you the type, whether it's a pond, whether it's an outlet, whether it's a road drain, whether it's a connector. Okay. And then it has a series of really weirdly named attributes. Okay, and it's got an underscore, a number, DR_2. So basically, what that is telling the model is, in this case, pond 5 is actually let me find another one. Point LP238. The next downslope node is LP239. The next one is LP57. So for example, here, let's start with LP87. It's right here. Flows down to LP246. And then from LP246, it joins runoff that's coming from above and sediment, and then goes into LP247. From there, it gets to this road, flows along this road, makes it to LP89, and then eventually leads into CST28. Okay, so again, these are manually being entered. That's why I tell you that this is still not ready for prime time. Again, in Culebra, it's much easier, right? Because we have less roads. But how about the coffee farms? This is Hacienda Candelaria. 875 road drains. Okay, it's not even the connectors, right? These are only the exit points from the road network. Okay, so this is still this needs to be automated eventually, right? That's what I wanted to do. This requires so much time, and researchers, we're just nuts, right? So we can go ahead and do this, but you cannot expect people to spend the time doing this. Okay, and then you can see here how this is again Hacienda Candelaria. You can see how, right, the different road drains are actually being connected, right? And then what is connected is actually the attributes are the ones that make those connections possible. Okay, and this is still in the works. This is something that I've been working on for a couple of months now, right? Whenever I have the time, right? But you can see how the database is being built. Okay, and you can see, right, this is relying on topography and the LiDAR DEM to drain those points and make the connections. Okay. Yaciel, how are we doing with time?
We have 40 minutes.
Okay, we're good. And then we have, right, the ponds are identified as points in that in that database, but then it also has a separate table, which basically, right, for the pond name, this would be the ID that it has on the point database, and then it has the volume of the pond. Okay, this is something that the user can change. Okay, and one thing that I do is the result of let's say that I want to run the model for a month's worth of rainfall. The results of the first storm, they tell me how much sediment accumulated on the pond, and then I subtract that amount from this. So I keep editing manually this database. So the next event, the trapping efficiency is going to be less. Okay, so we can actually do this with RoadConnect. Okay, and then the volume, right? We use surveying equipment to actually measure them, and we're going to be trying to use LiDAR actually to measure some of these as well for Culebra. Okay, again, I don't want to spend too much time on this, but right, it needs a series of folders, right, to be pre-created. And most of them is startup empty, right? The only one that actually you need to have some information is this is where all of those shape files on the pond database are saved. Everything else is going to be used by the model, and it's going to be throwing information there. And again, right, you need to be on the C drive in order for this to run properly. If not, the model is going to get lost, not be able to find the information. Okay. It's built on a model builder. Model builder automatically creates a Python code, but I don't even look at that. Model builder is a very visual way to create these models, and it's a series of modules if you want. Okay. In total, it's what, 10, 13, okay? There's a series of models. There's one module that actually calculates road runoff and sediment. Okay, basically just takes all that sediment from the roads, right, and tells you, okay, for this event, how much sediment and how much runoff is generated by each one of those road segments. The routing ones are the ones that are passing sediment and runoff downslope or downstream. Okay, and then these last two are basically just assembling the outputs. Okay, this is the road runoff and sediment routine. Okay, it calculates discharge and sediment based on user-defined storm rain total, right? So basically what I showed you earlier, how do you calculate runoff using the runoff coefficient, and how do you calculate sediment based on erosion rate. Okay, that is what it does. It goes through a series of, this is how Model Builder actually sees, or how the interface that I use to create the model. Okay, and basically just, right, it creates some fields, right? So it modifies the attribute table, makes selection. So basically what this is doing is just, okay, this is a road of this type. I am going to apply this erosion rate to that type of road. Okay, that's what's basically doing. And then basically just organizing that information back into the attribute table. So that's basically what it's doing. And then when you start the model, basically they'll ask you, okay, what is the rainfall size? What's your storm size? So this is where this is the only time that you actually have to an ability to interface with the model. This could be 5 millimeters, it could be 100 millimeters, okay, depending on the storm size that you want to model. The routing routines, again, I sort of explained this already, right? But it tries to connect how much of the runoff generated at a point, right? Or reaching a drain actually makes it into your destination, right? And is able to combine, right? Is able to combine different drains if they actually coincide in space. Okay, so this I can the ability of runoff and sediment generated at this point to make it to the coastline does not only depend on the potential or the volume of water, okay, and the length of that flow path, but it also depends on what, if there's any other contributions, right? If this is very small, but still makes it over here, and this is huge, then this has a higher potential to making it down into the coastline. Okay, so again, that's basically what I'm showing here. The potential from A to E depends on the potential from B to C to D, and from D to E. Okay, and it combines all sources. Okay, and you can see how complex this gets in some landscapes, especially in coffee farms. Okay, and right now we have up to 10 levels of node-to-node connectivity, right? So we can have 1, 2, 3, 4, 5, 6, 7, 8 connections before it makes it into the coastline. We'll see if that's enough for the coffee farms. I believe it is, but we'll see. Okay. And then it just assembles the outputs and the tables and the shape files that that is going to put together. Okay. Types of outputs that it produces. Okay. And this is actually an input, but I'm just want to show it, right? I mean, this is what we did in Cabo Rojo. We had rainfall data from May all the way to the end of July, mostly, or early August, and these are the individual events that we model for. Okay. Now, one potential output, and again, this has to be still manipulated by the user, right? There's not that the graphs come out that automatically. That's something that you really cannot do automatically from ArcGIS. Like this is something that you need to export into Excel or whatever package you use. But these are examples of watershed, a given area or farm scale outputs. Okay, is the total amount of runoff that is generated, or a total amount that actually makes it into the sinks. Okay, so again, cumulative runoff, right? This is the total runoff that was produced by the entire area that we modeled in Los Pozos, right? So you can see just one event, just very little runoff, and then a lot of runoff was actually generated. And then you can see, right, very little response to this event, and then a larger event, a bigger response, okay? And the same thing with sediment. Now, here we can differentiate between the amount that was actually produced, generated by the roads, and then the amount that actually made it into the coastline. So you can see only a fraction of the sediment actually makes it into the coastline, okay? And then here we differentiate between the coastline and the wetland because we have the Boquerón Reserve right there. So we differentiated that. Okay, and then the same thing for the ponds. Okay, you can graph how much sediment is actually accumulating in each pond, or you can simulate that. And then you can calculate, okay, according to the original volume, how what's the proportion of that original volume that's actually being occupied by sediment. Okay, and this is, for me, this is really, really useful. Okay, because it gives you what? It gives you an idea of the management plan for each one of the ponds that you have. Now, the most striking part of, right, and this is right, this is ArcGIS, or especially explicit type of model. Okay, you can also show and display your results graphically in a map. Okay, and there's two types of results that come up from the model. One of them is how much is actually reaching each one of the sinks. In this case, right, every one of those points is a point where the landscape can actually force some runoff into the coastline. Okay, and then you can color code them. In this case, right, megagrams or tons of sediment. So this is a very small event, only 4 millimeters, barely generating runoff from the roads, but still you have a bit of delivery happening, especially at this point, and especially at this point. Okay, so your sink, okay, there's a result as a point database that tells you how much sediment is reaching your destinations. Okay, but also, and anything on the that has an X, it means that there's no connection, there's no runoff. Okay. At the same time, you can actually show and display the sources of that sediment in terms of which drains are connected to the coastline. Okay, so again, here, right, this is a very small event. Might be a bit of connection somewhere, but it's very hard to tell. Let me crank it up 10 times. Okay, this is a 40 millimeter storm. Okay, and then you can see, right, this remain green, maybe just a very short road segment that is actually connected to that. Okay, some in yellow. Again, we're talking about tons here, right? So this is a significant amount of sediment. And look at this, boom, 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 boom. Okay, so again, this is mostly reaching wetlands, so maybe we don't care about coral in terms of coral reef protection, but then maybe we do care about wetland protection here. Okay, so you can see right immediately, right? There's some hot spots that show up in terms of where along the coastline a lot of the sediment is expected to be delivered. But also what? Hotspot in terms of road drain. Okay, so maybe this road drain is accumulating a lot of the sediment coming off from this series of roads. And that is what's making that a hotspot in the coastline. Okay. Same thing here, right? We tend to think that maybe something that's very close to the coastline is going to have a high potential. No, you can see, I mean, these are very small. Okay, but look at this one. For some reason, I really cannot tell you, I can't remember the details of this, but maybe that drain actually forces runoff into this road, and then right, that's an easy pathway, right? There's no cost to flowing along the road. Okay, and then delivers to this point and then goes in there. Okay, so there's a lot of contribution of sediment that ends up here that is coming from these upper parts of this micro watershed. Okay, again, and then you can see, right, there's a bunch of roads here that are not contributing anything. Okay, so a lot of all of the runoff and sediment is actually stopping before it gets anywhere close to the coastline. Okay, very useful, right? That you can actually start selecting priority targets for erosion control approaches. Okay, that's it. We have time for questions, discussion. I'll be more than happy to answer questions now. You got my email here. Again, we'll distribute this PowerPoint with you, and then we'll also distribute the recording of this PowerPoint and my presentation with you at a later date.
So thank you, Carlos, for a great presentation. I know all the hard work that this has taken. So with that said, if anybody has any questions, this is the moment for opening your microphones and your cameras or putting the questions in the chat.
There's a comment there about the RoadConnect link, right? Okay, Loderai, which area are you planning on modeling, or would you like to model using RoadConnect?
Hi, none.
Okay.
I'm not thinking in any area. I was just curious about if you have a minimum to add upon in the model when you show the table in ArcGIS. Do you have a threshold to add that pond, or
To add which
you have the volumes per each pond, right?
So each pond
So-
has a capacity, right? The volume is the capacity, yes.
Exactly. So do you have a minimum? So to add upon, maybe if it's too small, you don't add it to the model. Or if it's too big,
That's
or
up to the
how
user.
does that work?
That's up to the user, right? We have, I mean, the equation will take, I mean, the model will take it. The equation uses the volume. Whether it's actually represents the conditions or the sizes that the original equation from 1953 was designed for, I don't know. I do not know. You see, But in theory, yes, yeah, you can have a pond. You can have a pond that has a capacity of 1 cubic meter, right? And then you fill up really quickly, and then what you do. That's a you see, this is where the discussions is really important, because I want to make sure that if the pond, I haven't run into that situation. Okay, what if the pond fills up, right? What if the volume of the pond is actually 0? I don't know. I would need to look at the equation whether it actually tells you trapping efficiency is 0. I don't know. If not, I need to do like an if statement and say, okay, basically trapping efficiency is 0%. Okay, so you see that is when I sit with it, I need to make sure of that, right? You see that's why I don't want to create a link because then it can go wrong, right? It can give you really wrong. I mean, it might give you like a negative, right, value or something like that, right? So that's right. That's something that I need to think about, right? And then basically I need to plug in a 0 value for volume and see how the equation solves that. But
Thank you so much.
Yeah.
Awesome.
So do we have any other questions in the audience?
Just a quick question. So this is an event-based model.
Correct.
And if these ponds are trapping sediment, would you just, if you wanted to do subsequent events and look at how the pond volume changes, would you need to manually update those pond volumes to represent the newly trapped sediment?
That is what I've been doing so far, Michael. That's exactly what I do. So right, there's a product that comes out, tells you this is the amount of sediment that was retained by the pond during that event, and then I use that to subtract it from the existing volume that remains. Okay, again, at some point I wish to have someone to do that part of the model. That's where my limitations are right now in terms of programming, right? But I'm sure it's very feasible, but you can feed it a series of events, a year's worth of events, right? And then let it run, and then do that sort of calculation on its own. At least that part would be solved. Okay, but the model is not there yet, but you can do that, right? And that's exactly what I showed you there, is just that accumulation, right? So manually adding or subtracting those volumes from the remaining capacities. And you can see, right? And one of the things, I mean, and that's the detail. You can see at some point, even if it's not full, it's just totally inefficient. And I don't know what that number is, and that depends on how much runoff is actually entering into the pond, right? It might just say, basically you're trapping 2% and it's half full, but just because the volume getting in is just so large. And it made sense, right? We actually that was the way that we validated the model, right? For Cabo Rojo, we had those detention ponds. We ran the model for the period of time where the detention ponds have been active since they were built, and up until the point when we surveyed them. And for 3 of the ponds, it made sense. For 1 of them, it didn't make sense, and it was because that was the main access road, and then traffic actually affects erosion rates. And that was our hypothesis as to why that one actually it filled up too quickly for what the model was saying, but it was a hot spot in terms of sediment accumulation.
Thank you, Mike. So Carlos, from the research we have done, we also have identified that cut slopes are a very important sediment source. Do you see feasible that in the future, this model can also integrate cut slope erosion?
That's a really good question, and a very hard one to solve, to address. First, you will need either as part of your road shapefile, you will need some cut slope characteristics,
Mhm.
size and substrate and whatnot. We have very limited data on cut slope erosion. That's another thing, right? We only have one farm and then some work that I did in St. John, so we don't have anything else. So that's one thing that the production part is still needs a lot of work in terms of developing the metrics, the erosion metrics. The other thing is that what percentage of the cut slope material gets integrated into the runoff so it can be actually carried out, and nobody how do you do that? We don't have that capacity. We
Mhm.
simply do not have that capacity. Nobody has done that. People say X%, right? It's just it depends where the cut slope is to where the water is flowing. That's basically what and the mechanics of that and the ability of runoff to carry sediment that's piling up on the bottom of a cut slope. We don't have that. So for now, I would leave it out and just consider that it is only the roadway. Now, in coffee farms, and thinking a bit about right other components that are going to be added in coffee farms, you have right in Culebra and St. John, the natural hill slopes, very rarely you have runoff coming out from them. Now in coffee farms, you have the ability to generate runoff from the cultivated land relatively often, and that just explodes your connectivity.
Mhm.
Once that's going on, again, there's no cost. There's no cost for road runoff to travel downslope, right? And that is I need to find a switch in the model that allows me to account for that. If un predio, if an area cultivated land that you're forcing road runoff into is generating runoff, then it has no infiltration capacity left. So all of that road runoff is gonna connect, right? And we're gonna see those numbers really explode, right? But once we follow that threshold, you're gonna see, and that's what we're seeing in our flume data, right? That's why the flume is really important, because we see some events, right, that you see like a linear response in terms of runoff, and then there's a point in terms of storm size where runoff just explodes. And I believe, I mean, as we have spoken, that's because then there's more areas that are actually contributing runoff to that spot. Alberto and others from RCS, right? That's tied up to gulling, right? When you see those hotspots where you got a lot of runoff accumulating, that's where gulling can be generated. So I think the model can be used as a way to start identifying where gulling is possible, and then also landslides, right? So that's where I think the model is going to be useful for that.
Yeah, thank you. So, do we have any more questions? Yes, Lorelai?
Yeah, are you planning to, thank you, Yaciel, are you planning to update the model builder in ArcGIS Pro for ArcGIS Pro, or you're staying with desktop?
The next version is going to be on desktop, just to make my life manageable. But eventually, right? That's where you see that's the needs that I have moving forward, right? Right now, we're at the moment where we are generating the algorithms, the equations that are needed to run it in Culebra and to run it in Hacienda Candelaria, right? That's what we're doing, and then thinking for at least for the coffee farms, thinking a bit broader so that it's flexible enough so that I can use it in ultisol, oxysols, and then insectisols. So that's the plan, right? At least have the framework that allows us to do that. And then we're gonna build the databases, which we started doing that. And then you see that that's what is interactive thing. You have the data, and then you have a model that has some extra needs, right? Where do you fit it into the modeling? It's not totally clear, and that's why I want to navigate first in ArcGIS, and eventually, right, facilitate the use of the model for users, right? That's why it's at all is not ready for that. Facilitate the development of the databases. Facilitate also, as Michael was asking, right? Instead of having you manually to enter that information, update your database in terms of sediment accumulation and ponds, let the model do that automatically for you. So, but that would require like a grad student with funding to be able to do that. Yeah, it's a lot of time, and then somebody that really knows the programming environment as well, make it more efficient. Right now, I haven't been worried about processing time because I don't think it takes that much, right? I mean, and again, we'll see in the coffee farms, but I mean, Cabo Rojo had the very high density of roads, maybe a couple hundred of drainage points, and it was running really efficiently in my computer. So I'm not too worried about that, but just allowing the user to be able to apply it much more easy than what it is right now.
Awesome. Well, best of luck.
Gracias,
Thank you.
gracias. Thank you.
See.
Thank you. So if we don't have any more questions, I think we can finalize.
I'm gonna stop the recording now.
Okay.